1 second. Let me just pop over here. It went down for 2 seconds, and now it should be back up. Checking. Sorry. Yeah, so it should be good. Good. Okay, fantastic. I am so sorry about that. I screwed up. Pressed the wrong button. Hey guys, thank you so much for coming in. C252, Foldster, TV Chem, Merc, Sergio, Jamie Pine. Thank you so much for the raid of 47. I really do appreciate that. I hope your stream went fantastically well. I know it always does. You have a wonderful stream. And for anyone here who hasn't seen his stream before, please feel free to check it out. It's a wonderful place. CCNRD, thank you for coming in too. For those of you who are just coming in and you have no idea what this channel is, we are basically working on a large project known as the Algorithm Archive. Algorithm Archive is right here. It is an online repository of pretty much all the algorithms you can think of in every language you can also think of. So, for example, let's just pop over here. I'm so sorry, like, I was starting the stream, like it said, starting at 5 o'clock a.m. Japanese Standard Time, right? So, like, you know, I had to take a few minutes to get ready. I apologize for that. Okay, so for example, we go over here to Monte Carlo, you click whatever language you want, and it basically changes all the code boxes to match that language. We've got pretty much any of the languages that have been supported by the community so far. So here's emoji code, here's x86 64 assembly, here's Julia, so on and so forth. So they're all here. And the idea is that basically we work progressively towards adding new algorithms, new methods, all this kind of stuff into this book. In addition, we've got our YouTube channel, which is right here, youtube.com/user/LEIOSOS. Where this guy, let me just give it a second to load up. Here's that. Oop, sorry about that. This particular channel also is where we put all of the algorithms itself. So Gaussian elimination, split operator method, Huffman encoding, and here's the algorithm archive itself. And that's the overall goal, you know. Where's the implementation in lol code? I think we have an implementation in lol code for what is it? I want to say it is. Wait, what is it? I know we have one. Euclidean algorithm, maybe? Probably Euclidean. Here it is, lol code, right here. So how is I? Okay, I can't do lol code. Oh, dude, Foldster, you have a video out. Please feel free to link it. Let's see. I haven't seen it yet, obviously, but I do really appreciate it. So let's see. What do we have here? Bob Keck, Jamie, thank you guys so much for following. Really appreciate it. What about Shakespeare and whitespace? We do have whitespace for this one, whitespace, but we don't have Shakespeare. So if you want to implement in Shakespeare, please feel free to do so. Foldster, please also post your video. I'm very interested in taking a look at it. Not necessarily on stream, but I will take a look at it as soon as, you know, I can after stream, which will be at about 7 o'clock a.m. Japanese Standard Time. Ellipticum, thank you so much for following. Okay, so today, we're going to be working on something slightly different. So we will be putting a chapter in the Algorithm Archive for basically chaos games, iterated function systems. Iterated function systems. These are basically ways to take a random number or take a starting point and randomly manipulate them in decided ways such that we can create real structures. And by this I mean, for example, let's cd into project Simuleos and go into fractals. And let me just go ahead and run what we have for Sierpinski's triangle. 1 second. Sierpinski. This is a creative video in temp.mp4. Oh, cool. Thanks, C252. Open link. Again, I won't watch it now, but I have it queued up for immediately after I finish my stream. Okay, give this guy a second to create the video. It's taking just a second because we're generating a very large number of images kind of strung together, and we're kind of compressing them all into one 1920 by 1080 video. I know what you're saying, you know, we could do this a lot faster on the GPU by using, you know, OpenGL or something like this, and you're totally completely correct, but we didn't put that much effort into this, you know, so give it just a second to run. And while it's running, I'm going to get a quick sip of water and hopefully wake up just a little bit. All right, nice. So let's take a look at the video. So I'm just going to do MPV. Hopefully it's the last one. Nice. So here is, for example, the Sierpinski triangle. So what we're doing here is we're picking 3 points on the edge of the triangle. 1, 2, 3. Then on the inside of the triangle, what we're doing is we're saying, okay, well, let's take a random point and let's move that random point in some decided direction, right? And the direction will be towards one of the 3 random points, right? Or towards one of the 3 triangle points, right? So we take a random point and we say, all right, well, first time step, we're going to take this point and we're going to move it halfway between this point, or that point, right? So one of the 3 points, right? Then after that, we say, all right, well, now we're going to take that new point and move that halfway towards one of the 3 points. And then after that, we're going to take the next point and we're going to move that halfway between the next set of points. Does that make sense? So by moving these individual points closer and closer towards the edges of our triangle, we end up creating this triangle with triangles on the inside, explicitly because there are certain, I suppose you could say, actions that cannot be taken. And these actions that cannot be taken, right, because we're always moving towards one of the edges of the triangle, well, any of those moves that couldn't be taken would lead us into the interior of the triangle, right? Because we're always moving towards one of the edges, we always generate the edges of the triangle, if that makes sense. And sure, it kind of seems weird that we can generate these interior triangles simply by moving closer and closer towards these triangles over here. But in principle, if you think about it, it does kind of make sense, right? If we choose a random point here to begin with, it's going to move halfway up here, and then halfway over there, and halfway over there, so on and so forth. But it never really will fill in the interior of the triangle because it's always moving halfway towards another edge point. So kind of makes sense. Now, today what we're going to be doing is we're going to be working on the Barnsley fern, which is yet another one of these visualizations. We're probably going to update the Sierpinski triangle visualization before moving on to the Barnsley fern, and then go from there. Let's see, what do we have here? This is video. Oh, thanks. Wow, algorithmarchive.org this is what I wanted. Oh, cool. I'm glad you like it. Although I think I've seen you before in this chat before, Bear Todd, but maybe not. Maybe I'm wrong. You could speed things up by using a different encoder preset if it's not being uploaded. Yeah, so we're using FFmpeg. So I'm not really sure how this works underneath, if I'm being honest. So honestly, this library that we're using is called GathVL. The primary developer is the Gathros, who is here in chat. He says Simuleros couldn't handle the 47-party raid, which is true, and I do definitely apologize for being a little bit late on the uptake there. I was getting ready for stream. Since we are now, I assume, doing algorithms that require graphics, did we decide what we're doing in terms of newplot or language-specific graphics libraries? I remember there's a language discussion about it on Discord and GitHub. Yeah, this is the thing. There's a lot of ways in which we can create graphics, right? Our solution so far was just to output the data and then plot the data with a plotter so that we have some consistency. But maybe there's a way to do this differently. I don't know. We'll have to talk about that again. Let's see. Reminds me a little of the toothpick one. Yeah, I wasn't able to watch the toothpick stuff yet. Coding Train recently did a video on the toothpick stuff along with, I think, Numberphile. It's pretty cool. Coding Train, I met him at ThinkerCon. He's a really good guy. His name's Dan Schiffman. He's really cool. Since we know... Oh, wait, what am I talking about? Man, who was the madman who wrote the x86-64 ASM Huffman encoding in the algorithm archive? That might not have been Gathros, but Gathros has been doing a lot of the assembly code. So I want to say it could have been Gathros, but I also think it maybe could have been Gustorn. I'm not really sure. We can take a look. So let's cd into projects, algorithm archive, contents, and what am I looking for here? Cd into Huffman code, and we're going to look for, what is it, x86-64 ASM. Okay, L is here, and let's just do git blame Huffman.s. It looks like most of this code, oh, sorry for the yawn. It looks like most of this code is written by Gustorn. So that one was written by Gustorn. Actually, I'm pretty sure. Yeah, he was. You can just check the git blame. That's the nice thing about git. Okay, so let's go ahead and add some color to our Sierpinski triangle that we had before and modify a few small scale things, and then we'll go from there. That's some next level dedication. Look, I'm gonna be honest. This whole book is probably the most amazing thing I could possibly come up with. Like, I know. There's so many people who are making games, and they're like doing all these like very useful libraries for people and all that kind of stuff. But the algorithm archive, for some reason, just every time I think about it, I just get excited about it. I don't know why. It is that way. You know, it just combines like literally all my passions. It's like writing and community involvement. It's just like programming. It's everything. It's so cool. And I think like this is one of those things that I just want to keep going. And when you say next level dedication, it's so cool because we have like the entire community working together just to put new algorithms in the archive and new implementations and discuss things that we have already in there and say, hey, the Python code isn't good, let's update that, you know? And it's just great to have so many eyes on the same single project and all just kind of trying to make it slightly better, one step at a time, all just trying to make it a little bit better here and there. And it's so cool. I think on Christmas Eve, my time, which is going to be, I think the 23rd of December for most of you guys, I will do a long stream, I'm thinking about, where I just get up at 5 in the morning like I normally do the 5 to 7 o'clock time, but then I maybe double that time or even triple that time if I can manage, where we're just working on updating the algorithm archive. And I know that sounds like a really weird video to do on Christmas Eve. It's just that Christmas Eve is the first day I have off in a very long time. And so I kind of want to spend the time just working on stuff that I want to work on. You know, it's been forever since I've had more than 2 hours a day to really work on, I suppose you could say, stream stuff, you know, and it isn't really even stream stuff, just work on a project that I enjoy working on. And so that's something I'm really looking forward to. So I know it's not really Christmassy themed, but I do think I want to spend the 23rd of December your time, 24th of December my time, just updating the algorithm archive and going from there. CCC, NRD, thank you so much for following, really appreciate it. All right, so we're going to go ahead and CD in this terminal, and we're going to CD in projects. Oh, come on, dog, projects, Simuleos, let's go, Fractal. And I think we're in the right directory, but I'm going to open up another terminal over here. So let's go ahead and do that too. Oh, hello. So the main thing we need to update here is basically adding color into the Sierpinski triangle, and then we want to also maybe make the dots on the outside of the triangle a bit smaller. So here's the visualization one more time. And I think that these primary dots could be a little bit smaller, and we could add color and stuff like that. So there's ways to make this a little bit cleaner. Also, in terms of timing, we need to update the timing such that all of the interior dots appear after the 3 exterior dots. And then we probably want to draw the first couple dots separately. But this is a timing issue that can be very easily solved. It's not that big of a deal. Speaking of Python code, I think the Python implementation of Thomas algorithm could be changed so that it's not a destructive function. Yeah, please feel free to just either open up an issue or create your own pull request, and we'll discuss it. I know that we're a little bit behind on pull requests, and that's kind of the point of the Christmas Eve stream, to get through as many of these pull requests as we can. I'm just behind because of a bunch of other stuff. Just work, all that kind of stuff has just been wearing me down recently. But I mean, it's always wearing me down. It's just one of those jobs that just takes all your time. So let's go into Sierpinski. Here we are, .cpp. And so we have this compilation instruction. Let me just make sure we do have. Yep. So the compilation instruction still works from last time. And let's go ahead and go. So we have black, white, and gray. I had been using the gray color for interior points and not really coloring them in. So let's first start by lowering the size of these points in here to 5 by 5, I believe. So let's do 5 by 5. I'm also going to pop in here and add an additional integer up here, which is basically going to be the number of points on the interior of the triangle that we draw at the same time. Before, we've just been drawing some arbitrary number, which has been 10. Now we're going to be drawing I don't know, let's say bin size. Something like that, okay? So now we're going to be reading in bin size, and down here all we have to do is change this guy so that we're dividing by bin size. Alright, now the last thing we need to do is add in some color and basically change this function up a bit. Ah, dag nabbit. Hate when that happens. Alright, let's keep going. Okay, so now we're going to pop down here, read in bin size. I think for now, the bin size is just going to be 100. Not too crazy. And in here, we're going to go ahead and update the color a bit. So let's see, we have add animator. So we're going to have to add an animator for the color too. No, in fact, I don't think we do. Because we're reading the color into each individual ball, and we can probably just change that color. So let's pop up here, and let's just go ahead and change the color here. So we're going to say color is going to be equal to... let's see, how many points are we generating? We're generating, I guess 10,000 points, right? So let's go ahead and say we're going to be smoothly transitioning from blue to green. Oh, how about from blue to red? So this is going to be color is going to be equal to 0, 0, 0, 0, 0, 1, 0? Wait, how do we define colors? Okay, so there is an alpha value. Nice. Okay, so 0, 0, 0, 1. All right. So this is going to be the blue color, and then we're also going to have a 1 over here. And so it's going to be 1 minus, and I suppose it's going to be... Wait, I have to think about this. So this is going to be 1 minus whatever we had before. Head to pack. Where are you going, Foldster? You going on a trip for Christmas? If so, have a wonderful trip. So it's going to be 1 minus 10,000. Actually, n is what we probably want here. N. How about I times n divided by... No, I divided by n. That's what we're going to want. And this other guy is going to be 1 minus... I suppose it's going to be n minus I. 1 second. N minus I divided by n. And I think that should gradually change the color between, looks like blue and red. So let's go ahead and do a compilation here. Color equals, I forgot to give a name to the color. So we're going to call it ball color. And we're going to pop down here and change this to ball color. Oh no. Pop down here real quick. Going to your parents' house? Nice. Okay, so I'm not gonna lie. I just made chocolate chip cookies. I just made chocolate chip cookies given to me, like, I suppose, with the recipe provided to me by my grandmother. They turned out pretty well. I'm a fan. But yeah, like Christmas, holiday season, it's for the family. Go home, visit the family, enjoy your time. Like that's the way I see it. I know, I don't know. Like I know some people have love-hate relationships with their family, but just come on, it's Christmas. You gotta at least video call them. Just do something. Talk to them. I don't know. I mean, I'm gonna be doing the same thing. I will probably be streaming on Christmas, but I have no idea what I'm gonna do. And I know I want to do something holiday themed, but I have no idea what kind of holiday themed programming project we can do. I mean, we're already trying to draw fractal Christmas trees, and it's turning out okay. But you know, we're super far away from it. Like honestly, when we're making the video this Sunday, or when I'm making the video this Saturday, what will probably happen is I will probably try to describe the fractal flame method as we have implemented it, and then I'll say, hey, we did our best to create a fractal flame, and just show that we didn't do anything, like the fractal flame we created was bad, or the fractal flame I created was bad, and then just show that Foldster was able to create a tree of Sierpinski triangles, which was pretty cool. I don't know. If you have a fractal Christmas tree that you want to take a look at, oh, those all just turned out pink, didn't they? Huh. I mean, don't get me wrong, like it is slightly better, but they're all just pink. I was hoping for a smooth transition between blue and red, and that is definitely not what I saw. They're all pink. Okay, well that's good to know. So let's take a look and see why they're all pink. So we're going to define this ball color in here as 1 minus I divided by n. What probably happened here was this was automatically floored because this was integer division. So let's go ahead and define this as a double there. Here. And let's also do the same thing over here. So this is going to be n minus I. So I guess we're just going to say double. And I think this should... The compiler warned me about this too. So let's try this again, Sierpinski, and then we'll try MPV when that's done. Would you like me to PM you my fractal Christmas tree? I think I already have yours, but please feel free to send it. If anyone here has a fractal Christmas tree, or any type of Christmas tree that you've generated via code, please send it in as soon as you can, and I'll go ahead and put it in my next YouTube video that's coming out on Sunday, my time, which will be Saturday for most of you guys. On the road, phone wireless can't handle the stream, so I'm on audio only. Oh, fair enough. I didn't realize you could do audio only. Let me check over here. 1 second. What do we have? Settings, quality. I don't even have quality options today. That's fair enough. Not a big deal. On the road. I thought you wrote x86 ASM Huffman. Realized it was guest run. Yeah, fair enough. So what I was going to say was that, yeah, if you have a Christmas tree, procedurally generated Christmas tree for the upcoming kind of sort of Christmas fractal video that's coming on, please feel free to just go ahead and send it my way, and I'll do what I can to put it into the video as soon as possible. Ideally, you get it sent to me before the end of Saturday, my time, so like probably Friday afternoon, your time. So let's go ahead and take a look at MPV. Okay, there we go. So we go from blue to red. Now the question is, should we modify the color based on location? I'm actually kind of okay with this. I kind of like the blue to red. Let's see. So let's go ahead and modify this one more time. We're going to G down here. And we are going to, I believe, double the number of points that we're running with here. So let's do 2. Let's write this. Go into G++. And then we're going to run ./sierpinski. And give it a second to run. I don't know how long it's going to take to run. No idea. I just suffered through the ugly chat for nothing. I'm so sorry, Gathros. I mean, I don't know. It's random whether I get quality options or not. I would really like to have quality options all the time. Again, that was kind of why I wanted to be affiliate in the first place. But hey, it is what it is. You know, sometimes you can't get quality options all the time. And that's fine. It's not that big of a deal. Okay, so we are going to watch this go. And then after this, we're going to work on the next visualization, which will be of the Barnsley Fern. So I'm going to create a few quick visualizations here. One of the Barnsley Fern itself. And then what I want to do is create a visualization of basically every single movement of the Barnsley Fern. And we'll talk about that immediately after the Sierpinski triangle is drawn. Again, if you've got any questions, comments, concerns so far, please feel free to let me know in the chat, and I'll do what I can to answer the questions and stuff as soon as they pop up. Let's see. Nice. Okay. Sometimes I just get notifications and there's nothing I can do about it. All right, let me get a quick sip of water, and then we'll go from there. Now, the thing is, I've got a feeling... Well, I don't know. I don't know what's going on here exactly. So we'll see what's going on. But I don't know how long this is going to take. I probably should have timed this. Oh, maybe it shows... No, it doesn't show time. I think that most of the time is spent with FFmpeg doing the video creation. I don't think most of the time is spent generating the individual objects and stuff like that. So I think we're okay with this setting. Do you not like the chat? I think the chat's fine. Sorry about that. The chat, I like the chat. Okay, so we'll give this guy a second to run, and then we'll take a look at it. I just got a feeling. I don't know why this is taking so long. I don't know. Did it take this long last time? Yeah, I think it maybe took that amount of time. MPV. Okay. So here we have all the points being generated. Yeah, I like that. That's good enough. Sure, the blue to red might be a bit weird, but hey, you know, it's fine. It shows the transition of the fractal with time. You can clearly see the triangles instead of triangles. And then you see the 3 points on the outside, which are clearly white. Yeah, okay. I'm okay with that. All right, so let's move over. And let's go ahead and add sierpinski .cpp, and we're going to do git commit. Modifying green to red would be more festive. Yeah, but for the Barnsley Fern, we're going to be doing green to red. Or rather, well, green to red would look kind of funny, but we're going to be doing blue to green. So I'm hoping that we'll have like kind of this reddish and then greenish. We'll see how it goes. So I'll take a look. So let's go ahead and do git commit, and we're adding sierpinski triangle updates. All right. So now we're basically going to take this and move it onto the Barnsley Fern. right, so let's go ahead and do, I'm just going to copy it, honestly. Sierpinski.cpp, move it to barnsley.cpp. All right, let me just go ahead and update it. So we have the appropriate compilation instructions and everything. CPP. All right, so this is going to be barnsley.cpp. Let's do dt dot, dang it, dt, dang it. All right, we're just going to do it this way. Barnsley.cpp. Add a couple dashes here. And just add the compilation instructions. So it is output Barnsley. And it's going to be output Barnsley.cpp. And we'll have to update it again. It's not too big of a deal. So let's go ahead and change the names here too, because I feel like changing the names to Barnsley. Sorry about that. Here. And let's just go ahead and look for the next sierpinski here and change this also to Barnsley. Now all we have to do is change the chaos game such that it has the appropriate numbers and stuff in it. It shouldn't be too difficult to do, I don't believe. So here we just change this set here to be what we want it to be. So let me go ahead and pop up over into VI. Ooh, hello there. Let's go ahead and quit there. VI. What? All right, I gotta be honest. I changed my terminal to Vim mode at some point. It is actually a bit different, and I keep running into issues with it. So ifs.jl, and let's just take a look at the Barnsley Fern. Here we have it there. And basically we have these chosen functions with some sort of probability, and then we just, oh, sorry for the yawn. We modify their x, y, and z location depending on the random probabilities here. So I'm going to pop down here. I'm going to add another else if statement. So let's do yank for yank, paste it down here. And now we just have to modify everything. So let's go ahead and get the probabilities first, and then we'll get the interior parts here. Here it is. So if the random number is less than 0.001, I'm sorry, 0.01. So it basically has a 1% chance of doing this transformation here. Oh, good. It's all here. Let's just go ahead and use that. Then it has a, let's see, 0.01. Oh, hello. Come on. I can type. Anyone who watches this stream knows I can sometimes type. Let's see. So we have less than 0.86. Okay. The next one is between 0.86 and 0.93. 93. And the last one's going to be between above 9.3. So basically we have 4 different transformations that we're going to be performing on our object. And for those of you who don't know what the Barnsley Fern is, let me just go ahead and run new plot, plot barnsley.gp minus. So it is a fractal that is essentially ferns on top of ferns on top of ferns. That's what we'll be working on here. So that's what the Barnsley Fern is. It's you know, here we have the primary fern here. And then we have these leaves that are continually generated on the edges. This is super easy to turn into something that looks kind of like a Christmas tree. So I'll be honest. The periodic stream stuttering, I haven't dropped any frames. The only thing I can think of is that this is an issue on Twitch's end where we have, I don't know how to put this, but we could be running into an issue where like maybe your internet can't handle the bitrate or something that I'm streaming at, but I'm streaming at bitrate of 2000, which is relatively low. I could try lowering it a bit more, but at some point you're just not able to see, you know, anything anymore. So, let's see. Looks like you're having it higher. What do we have here? Looks like you're using one of the higher. Nope, I'm definitely not. I'm using file settings. I'm literally outputting to 2000 bitrate, which is incredibly low. I'm not willing to go much lower than that. I mean, I had it at 1500 before, but I mean, I could try setting it down to 1500, but I'm not too willing to set it lower than that. Oh, for FFmpeg. Oh, I'm sorry, I misunderstood. Sorry about that. If I missed anyone in chat, I do apologize for that. Let's see, what did Gather say? Gustorn, quality options, red to red. If you're using Vim, install gvim, not Vim package on Arch, since you can use clipboard. Yeah, fair enough. Anyone else have issues with stream periodic stuttering? Yeah, so I think I'm caught up. I guess it's Twitch. I don't see any 200 megabytes per second connection. Can't handle. I don't see how my 200 megabytes per second connection can't handle a 2K bitrate. Yeah, right. I don't know either. Sometimes this happens. And again, like, I used to have quality options all the time, but now Twitch just doesn't give me quality options sometimes, which really does kind of suck. But there isn't much I can do about it. Okay, so that's what the Barnsley fern is that we're generating here. So let's go ahead and go and just barnsley.cpp. And let's just go ahead and update all these points. Now, unlike this guy over here, where I did basically a matrix transformation on these points, I'm going to have to modify this a bit. So let's go ahead and modify it now. So basically, the x location here is going to be changing dt here to 0.0 at all times. And the y position is going to be equal to 0.16 times the point's y location. Okay, so that's the first transformation. Let me go up here and let's define the vector point to be 0, 0 to begin with. dt comma dt, oop, hello. dt there. All right, let's just add 0 here and 0 there. And what I'm going to do is modify this so it's no longer if I is greater than 20. We don't need that for the Barnsley fern. Okay, so let's just go ahead and do d4. Oh, I'm sorry, 4x would probably be the fastest way to do this. Okay, cool. So let's see, what do we go from there? The encode might go faster if you use preset ultra fast, assuming that you've got a fast enough output device. Yeah, we could probably do this. I'm not sure of the choice of CRFFX encoding speed though. Yeah, I mean, at this point, I'm kind of okay with what we have. I do realize that, yeah, in principle, we could be a lot faster with it, but I'm okay with this right now. Let's see, what do we have? We have 1200 frames. Do we need 1200 frames? Probably not. We probably need... Let me take a look at this last video that we have, actually. So let me just do MPV. So all of these guys seem to be generated after that point. And this is at... Yeah, okay, so most of the video, actually. This is only 4 seconds in. So we could probably drop the number of frames here to maybe 500, 600, we'll say. We'll cut it in half. And we'd probably get the same video, ultimately, without really too much trouble. Does that make sense? Like, the video would basically be the same. All right, here we're going to modify the color too, so that this is now going from blue to green. So it's going to be 0 here and destroying the 0 there. Okay, so let's go ahead and get these transformations done. All right. So the next transformation is going to be 0.85, 0.04, negative 0.04, 0.85 times our individual point. Then we're going to add in a bit of a value from there. So here, let's go ahead and do the x modification first. So it's going to be is there a way, do we have point.x, point.y? This is already a vector, right? No, okay, we don't have the matrix multiplication. So let's go ahead and do a quick xxx there, and we're going to say point.x. This is going to be adding in 0.85. I'm just going to have to do the matrix multiplication real quick. Let me open up a separate terminal. Let's just do this. So terminal. Okay, and let's go. Nope. Let's try it again. Pop it over to this desktop. Tacnap it. Pop this over to the next desktop. And let's go. Okay. So the first guy is going to be 0.85, 0.04. So it should be 0.85, 0.04, negative 0.04, 0.85, I believe. So let me take a look at that real quick just to make sure I did that right. 8504, yep, that is correct. So this is going to be times x and y. And then we have an offset after that. So it's going to be 0.85, 0.85 times x, 0.04 times y. So it's going to be 0.85 minus, am I doing this right? 0.8 times my x, 0.04 times y, plus 0.0 minus 0.04 times x plus 0.85 times y. And this is going to be x equals and y equals, I believe. So x equals and y equals this. And then we're going to add in the offset to y. Oops, sorry about that. I hit the microphone. Just saying that the time token to encode the video adds up. Oh yeah, fair enough. Thanks a lot. Okay, I think this is correct. So we'll take a look at that. Honestly, I can probably just Google Barnsley-Fern. Let's take a look at that too. So Barnsley-Fern. Okay, so we have the Barnsley-Fern here, Wikipedia. And I'm pretty sure they give us what we need. Yeah, they do. So 0, 16y. Yeah, this is exactly what they give us. And these are the functions we need. So we might as well just take these functions anyway. It's just matrix multiplications that we have on top of our other system. Okay, so let's do that. 0.85xn, 0.04yn. So this is going to be point.x times 0.84 plus point.y times 0.04. Is that correct? Yep, so the next one's going to be negative 0.04xn plus 0.85yn. So this is going to be 1, 2, 3, 4. Delete that just because I can. And it's going to be, let's just go ahead and delete all of this. Negative 0.04 times pt.x plus 0.84 times pt.y pt.y plus, I believe it's 0.16. 1.6. So 85y negative 0.04x, and let's just do 1.6 here. Okay, so that's the first transformation. And this transformation is basically the transformation that creates successive leaves on the top of our fern. Now we have to create the first left and right fern. Coding FFmpeg and C is hard. I don't want to touch video encoder ever again. Yeah, I totally understand, and I'm not going to push you to do that. Okay, let's go ahead and delete these guys too. So dt comma here and there, and we're going to do dt that and that. Okay. And what I'm going to do is I'm just going to go ahead and copy this line here. So yank till that. I'm going to paste it here. Sorry, paste it there. And paste it here. And I'm also going to grab the same thing over here. So we're going to yank till squarely bracket. And then we're going to paste before. Oh, you that. Paste here. And we're going to paste there. Okay, so we're going to modify these as needed. So this next one is going to be 0.02xn negative 0.26yn. So it's going to be 0.2. What was the other one? 0.26. Yep. Is this a minus? Yeah, 26yn. The next one down here is going to be 0.23, 0.22, 1.6. 23.22, and hopefully that's correct. 2322 plus plus, correct. So the next one's going to be negative 1528. So let's go down here, 15. Put a negative in front of there, and then the next one's going to be a 28. And then the last line is going to be 262444. 262444. Something like this, and then delete the minus sign. Is that correct? 262444. Okay, so this should be the correct Barnsley-Fern. So I'm just going to go ahead and write this, and we're going to run it real quick. So let's just run, where's the last G++? There it is. So let's go ahead and modify this real quick so that we are running it with the Barnsley.cpp instead of sierpinski.cpp. And then we should go from there. Have you written this Fractal Flame chapter yet? No, there won't be a Fractal Flame chapter for this video. I just can't figure out how to manage my time properly to get that done. I guess I could enter that /Barnsley, and then we'll take a look at this once it's out. Okay, so as far as there not being an algorithm archive chapter for this particular video, I guess, I mean, in principle, I really should have an algorithm archive chapter for this video. I just haven't had the time to write it. Video with no chapter? Yeah, that was the plan. I mean, I can... Oh, hello. Grid extents? You are clearly not right. So let's modify this a bit. That was the plan, but I suppose I can... Go ahead and just remove some of these points in here. And let's not add these triangle points. Okay, fine. I guess I can write the chapter, but this means the video is going to be delayed. Well, I mean, that was the plan. Like I said this like weeks ago, you know, there wasn't going to be a chapter for this. Yeah, there's no way I can get the chapter out in time for the video on Sunday. I could spend Sunday writing the algorithm archive chapter, and then get the video out on Monday. But then the problem was I was planning to stream all day on Monday, so I can't put the video out while also streaming. Yeah, I could write a chapter after. In fact, I could spend Monday's stream writing the chapter. Why don't you make the video then the flame chapter? Yeah, I could do that. In fact, I mean, this video was supposed to be kind of Christmas themed, but if I'm being totally and completely honest, it's more about the Barnsley fern than it is Christmas trees. So I could just make this a general holiday themed video, and I could put it out slightly after Christmas, I guess. That'd probably be the best I could do here, to also get the chapter out. I mean, I'm kind of not going to be able to. Video with no chapter, Monday day stream, can't wait. Okay, so we can do this a couple of different ways. We could do this such that we do a video without a stream. Wait, what am I saying here? We do a video without a chapter. We can do that, which was the original plan, and then we just do a chapter later. Even in the video I mentioned already, in the video that I've taken, that I didn't really have there isn't going to be an algorithm archive chapter for this. But I can also spend Monday, which I'm working on algorithm archive updates anyway, writing the chapter for chaos games and stuff like this. And maybe that's okay. Maybe this is a good way to do it. Or we can wait to put the video out after the chapter is out, like I normally do. So those are the three options. One, we write the chapter first, put the video out later. Two, we do the chapter later, which we could do during the Christmas Eve stream, and maybe even during Christmas stream. I don't know. We could find a way to do that. And then three would be just no chapter. I do think that there does have to be a chapter, but the question is, when should we create that chapter? And that's what I'm not sure. There's never going to be a no. There will be a Fractal Flame chapter. But what I wanted to do was write a general chapter on iterated function systems, right? And so the idea was that, hey, this particular video, there isn't going to be a chapter on it because it's about kind of understanding the chaos game, which isn't necessarily, it's not necessarily an algorithm itself. It's kind of like one of those things. So then from there, I was thinking, all right, well, we have the chaos game. We have a video on the chaos game. Now let's go ahead and create a general chapter on iterated function systems and stuff like that, referencing the previous video. Hey Husky, Grion, ooh, okay, I cannot pronounce that. I'm so sorry. But GR3ON3YZZ, thank you so much for following. I'm going to call you Grion because I think that one is phonetically the easiest to pronounce, but let me know if there's something you'd rather go by. Let's see. I thought you were saying, yeah, okay. Let me just go ahead and write down the three options. In fact, let me just do a poll. All right, let's do a straw poll over here. All right, straw poll, strawpoll.me. I don't really know the difference between me and .com. I guess maybe I should use .com. It doesn't matter. Okay. What are we doing with our... What are we doing? Okay, so question. Chapter first, then video. Video first, then chapter. Stream chapter writing on Christmas Eve. Okay. Then what's the last one? Chapter first, then video. Video first, then chapter. Video now. General IFS chapter when it's ready. Don't know. Don't care. Okay. I guess I'll put something in there. Okay, so let's go ahead and create that poll. And I will send it in chat. Paste it here. Alright. Plus a greeting algorithm on top. CPU at 100%, resident sleeper. Can't play video games, resident sleeper. First world problems. What are you training a model? Doing spectral graph clustering. Feel your pain. Yeah, I've been there. So let's see, what do we want here? What we're going to do is we are going to modify this fractal such that it fits into our grid extents. So what are we going to do then? We have repost poll. What's wrong with that poll? Oh, were you just not here? Yeah, I can repost it. Wait, what was wrong with... Did I do something wrong here? Maybe I can do... Should I have clicked the share button? Maybe there's something wrong with the poll. I'm sorry. Okay, so what we're going to do is we're going to modify this so it fits into the grid extents. There's a lot of vertices. What is that? Almost 2 million vertices and almost 3 million edges? Nice. Good job on that, man. So we're going to say 0.5. So let's go ahead and multiply the x component by 0.25. And we're going to modify this by 0.1. And then we're not going to subtract out 800 points for y. We're going to subtract out 100 points for y. And we're going to see what happens. So let's go ahead and write that. And let's run the last G++, run Barnsley. And then we'll take a look at the MPV when it's done. Oh, lost reception for a minute. Yeah, fair enough. California Road Network. Yeah, that's how it is, right? All right, so let's give this guy a go. We're not going to be able to get a fractal Christmas tree done anyway. Like, this is just taking too long. Dang. That is unfortunate. So it looks to me like I'm going to spend the whole stream tomorrow trying to create our fractal Christmas tree. And we're probably not going to get very far. I mean, we might get somewhere, but not nearly as far as I want to get. All right, let's give this a go. Whoa, whoa, whoa. What are you doing, dog? That was not what I was anticipating this to look like at all. Let's see. So we're going to multiply this by... Why is that? Okay, so the x location should be... If the x location is 0, we want this in the center of screen, right? Okay, so if the x location is 0, the x location is 0, we want it in the center of screen, and if the y location is 0, we also want that at the bottom of the screen. So we're going to have to subtract out actually 1,000 points for the y. And now for the x, let's see if we can get that 0 in the center of screen. So it's, I see what I was doing wrong. This guy, I think, still needs to be 5. Minus 400. What does the minus 400 do here? So it's going to be the size.x times 0.5. So it's going to move to the center. Then we're going to subtract out 400. But what does minus 400 do here? Vi sierpinski.cpp. Pop down here. What did I do over here? I said minus 400. Size.y. So we also want this to be 0.5. Oh, I see what we're doing here. So now we're moving it down 400. So let's go ahead and move this down. See, it's 1920 by 1080. It's actually moving it down 400 is about right. And then we want to multiply this by, let's do 800 again. So this is what it was before. So this should move it to the lower bottom of the screen. This should move it to the center of screen. If it's 0, it's going to be all the way over there. So we don't want the offset here. And then this guy's going to be multiplied by a greater value. One second. I have to think about this. I'm just trying to get this fern into the appropriate spot. So this is going to be multiplied by 800 pixels would mean it's 800 by 800 from 0 to 1. So if I increase this, it should be bigger. So let's change this to 1000. And we're going to change this to 1000. This is just fudge factors, so it's going to be a bit weird. So let's pop over here, and let's go ahead and quit there, and let's run G++, Barnsley, and give this guy a go, MPV. Okay. I'm sad that you won't be coming with the Christmas tree themed competitor to Speed Tree. Yeah, I understand. I'm sorry. It's taking me some time to make this Christmas tree. I'm sorry about that. Max RAM usage so far, 4.7 gigabytes, seems good. Yeah, man, I use so much RAM. Okay, we have our tree. We just need to shrink it and then move it down. Okay, so how are we going to do that? So if we multiply this by... Actually, let's change this so it is 400. And let's change this so it's also 400. I think maybe I had my intuition wrong there. Barnsley, and let's do MPV. And let's see. So the problem is the Barnsley fern naturally goes beyond the extents of our 1x1 box that we had allotted for it. I don't really remember how big the Barnsley fern is exactly. So I'm just trying to figure out what we need to do with the space here such that we have the box, like we have our fern being drawn kind of at the appropriate location. So we're giving this guy a second to run and we'll see what happens. This looks, I guess, better. Yeah, I mean, it certainly looks better. So let's do 100, 100, and let's do Barnsley. And hopefully this should have the entire fern in our view, and then we can look from there. Clustering graphs into communities based on eigenvectors of the Laplacian matrix from the adjacency graph. Huh. Let's see, what do we have here? I had a question for you. I will probably need more RAM in the future, but will 8 gigs be enough for machine learning? Okay, I don't know what just happened. Yeah, I don't know what just happened at all. Y seems to have stretched. No, I don't know what just happened at all, actually. Minus plus 100. What? Minus 400. We're going to want to do plus 400 here. Plus 400 there. Alright, so there's something clearly wrong with our Barnsley fern that we're generating here. And I'm not exactly sure what that is. So I think, oh, I think I know what I did wrong. Let's try this again. 1 second. Trying it one more time. And we'll see what this generates. It looked like we got the stem right. And it looked like we had one of the leaves right. But it didn't look like we had the rest of the fern. So we'll see how this goes. Oh, let me get a quick sip of, or let me get a quick sip of water. And hopefully, this does something that we want it to do. Okay. Give it a second to run. My old work university spoiled me with a $1,000 GPU. Yeah, I know how that feels. I'm really spoiled by my current university. We were at a advanced HPC user group meeting. Oh, there's the whole fern. Nice. I'm liking that. That's pretty cool. Okay, so let's just lower the fern just a bit more. So we're gonna lower it by 500. And I think that'll mean that we can see the whole fern. And we can actually make the fern a bit larger, so let's change this to 200. All right, and let's just do a quick G++, Barnsley, MPV. And let's see, we should have the whole fern being generated here. Hey Red Whale, what is up? Thanks so much for following, really appreciate it. But yeah, so I was at an HPC advanced user group yesterday. They were talking about all the fancy new things they're going to be adding to our cluster here at OIST, and it just made me realize how lucky I am to be at OIST, you know, how lucky I am to be here, and having all the computational resources I need and all that kind of stuff. It's really cool. New Zealand pride. Is anyone here from New Zealand? It should be what, 8 a.m. in New Zealand time? Oh, maybe almost 10 a.m. in New Zealand time, actually. I'm not sure. I think they're 4 hours ahead. Meanwhile, everyone else is super far behind, or something like that. I'm not really sure. Comment says, implementing Sierpinski triangle. What comment? Oh, yeah, you're right. Let's go ahead and modify that. There's the whole fern. Look at that guy. Nice fern we got going on there. Cool. Okay, I'm a fan. I think it looks okay. There's our fern. Okay, so I'm going to go ahead and commit this to just saying we have a very simple example of the Barnsley fern working. And now we just have to show what each of these transformations do. And hopefully we can create some sort of clear, understandable... The problem is we have basically these 4 different things that are happening in this Barnsley fern. We have the initial stem, we have a right leaf, we have a left leaf, and then we have successive leaves over here. And so what I need to figure out how to do, what I need to figure out what to do, is basically explain in a visual sense what it is that each of these 4 transformations are doing. It's clear that the first transformation is just making a stem. It's clear that the second transformation is making one leaf or another leaf over here. What's not clear is these successive branches to me. So what I need to do is basically take a random distribution of points, modify this random distribution of points with each of the transformations and show exactly what's happening in a visual sense, with the hope that by doing these transformations in this way, we can more easily understand what it is that the Barnsley fern is actually doing with each of these 4 steps. And so that's the whole point. We're trying to get a better understanding of how the Barnsley fern works. So let's go ahead and change this to Barnsley fern. DD there, implementing nice fern, Deuterino. Thanks, Bottercake. So we're going to say Barnsley fern. $, Barnsley fern. Okay, so let me go ahead and commit this. So git commit barnsley.cpp. Ooh, hello, git add barnsley.cpp. And git commit -m. I'm adding simple example. Fern. Probably should end that. All right. What do we have here? Not super familiar with Ryzen and its chipsets. Does chipsets on the motherboard allow for overclocking? How well does it run? How well does that Ryzen chip, I guess, overclock? Let's see. Implementing Sierpinski triangle. Thanks, Zentatsu. Let's see. You can save a bit with a 650 watt power supply. Next gen Ryzen will be insane if the leaks are true. So honestly, one thing that did very much impress me in the HPC user group that I was at yesterday, user group meeting or whatever, is that Ryzen CPUs seem to be much more powerful, just per core, than Intel CPUs, let alone the fact that they have more cores. This was very impressive to me, and I'm very interested to see where they go in the future. It just seems like it is a good place to go. But can it run Doom? Probably not. Doom is an incredibly graphically intensive game. I tried running it in my terminal the other day, and it just didn't seem to function right. Oh, but there is ASCII Doom. ASCII Doom is amazing. Let me check the results of this survey. Video now, general IFS chapter when it's ready. Don't know, don't care. Okay, so it seems like most people are okay with just getting the video out now. But again, we only got 6 votes. So if you want to vote, please feel free to do so. Here's the link one more time. And again, this particular, let me see. So this particular, I guess you could say, poll is seeing what we want to do with the upcoming video and stuff. So I know Gathro specifically said that he would like to have, or maybe I misunderstood, but some people here in the chat have specifically said that they would like the chapter out sooner than later. What I was thinking about doing was just getting the video out now and then doing a separate video and a separate chapter on IFS systems in general, linking back to this video when that comes out. But give me time, because this isn't like a required, it's not like a necessary algorithm. So the video first chapter when it's ready is the one that I think most people voted for. Chapter first, then video. Okay, so we got at least 1 vote for that. But I think most people are okay with this so far. But we'll take a look at this again in just a bit, once everyone's voted. Let me show you ASCII Doom. I know it's a thing. ASCII Doom. The only criticism I have of ASCII Doom is that it doesn't run in my terminal. Let's see. I'm not going to be done of gaming on it. Okay, so let's open up barnsley.cpp. And I'm going to create a new scene in here. So we're going to say void And I guess this is going to be Barnsley transform. All right, and we're gonna say camera ampersand cam scene ampersand world int n, and then transformation type int trans. We'll call it T type. All right, I know I should be using better notation here, but give me a break. So we have black, white, and gray. We define these to begin with outside of this, and I don't think we even used black, white, and gray. So let's look for black. No, we didn't. Let's just go ahead and delete these three here and recompile. Here? Yeah, of course we didn't. Okay, so what we're going to do is we're going to generate a random distribution of points, and then we're going to move each of these random distribution of, like each of these points into another location, right? Depending on the new transform. So what we need to do is start by creating a vector, std vector of vec, and this is going to be equal to, I guess we'll call it points, and we're going to make it size n. Something like this should work. Now we're going to say for int I equals 0, I less than pts.size plus I. Pop down here, and we're just going to randomly allot each of these guys. So we have the vector of points n defined here. So we should just be able to say points of I is going to be equal to rand. In a similar way, I'm not going to worry so much about like Mercine Twister and stuff like this. I'm just going to go ahead and just create a very simple random number here. I'm not worried so much about this being incredibly super random. I'm just trying to get a visual output, you know. Let's see, faster OC single core speed plus 23% on similar price chips. Okay, interesting. I'm not going to be done gaming on it. Dude, I love ASCII Doom. I'm glad. ASCII software raster is pretty neat. Yeah, honestly, I really want to make some ASCII games. I know that sounds really dumb, but ASCII games are somehow my favorite types of games. I don't know why, but I'm always just so happy when I'm playing games that are like low resolution, low bit, like just like the most basic game you could possibly think of. These games are just, they are genuinely fun to me. Like for example, Rogue. Love this game. You're just a slow guy. I'm fighting a hobgoblin. I just died. Probably shouldn't have fought the hobgoblin, but that's fine. It's just a nice game that you can play. It's just, I don't know. They're fun. There's also the skiing game you can play. It's just nice. There's a lot of fun games. I've always wanted to create a terminal game. I don't know why. I don't even know if this compiles, like if I'm doing this correctly. So let me just go ahead and press return to continue, and let's G++. Whoa, look at that. I know how to create a random distribution of points, apparently. So now we're going to basically create a vector of balls that we're going to be working with here. So we're going to randomly generate these points, and we're going to put them into an appropriate location. So like before, we're going to basically create, oh, actually, I don't think I have this defined anywhere because I deleted it just a second ago. So let's go ahead and create that vector too. So we have the points there, and we're just going to create std vector, and I think it is std shared pointer, but let me just go ahead and open up vi. Gathvl, yep, vec. No, I'm looking for viz test. And let's see, what do we have here? Oh, that's also not what I'm looking for. vi //scow. Oh, Laos curve scow.cpp, and let's see if we can find our vector of legs. There, that's what I'm looking for. Shared pointer of ellipse. And I guess we're gonna call this, what should we call it? We will call it, we could call it distribution. We could call it, yeah, this is a bit of a problem, right? Like we have an idea of where all the points are. I don't know. What do we have here? Dwarf Fortress? Ha. Yeah, man. You should make a terminal game. I do want to, I just don't have time, you know? I was thinking about making, there's this thing. Let me show you this thing. One of my favorite things in the world. It's not, I mean, maybe not my favorite things in the world, but it's called ASCII Aquarium. It is just an aquarium in ASCII. That's all it is. It's a bunch of fish. You know, you got this boat up here. There isn't anything else to it. It's just like an ASCII animation that you can run from your terminal. This is it. I was really wanting to create like an ASCII New Year thing where basically like it just says Happy New Year and there's like, you know, fireworks appearing in the background, people walking along the bottom or something like this, you know, just some sort of like animation, ASCII animation, just something super basic like that. And I really wanted to make one for New Year's this year, but I just don't think I'm gonna have time. Look, I mean, there's ducks up here, they're quacking. Look at these quacking ducks. I'm sorry, I've been wanting to do something like that for a while, and I just haven't found the time. Okay. SL is my favorite ASCII art related program. Of course it is, because it's always frustrating when you accidentally mistype the SL command, and then this slow ASCII train just goes across your terminal, you know? It's fun. ASCII Tetris, I don't have that one installed here. There's also ASCII, what is it? ASCII Pac-Man. That's also another thing. Okay, so we're gonna call, what are we gonna call this group of ellipses here? Let's call it, we have the points. Let's see, this is gonna be the points in, what are we gonna call them? It's a random distribution of points. So maybe, ellipses? I don't know what to call them. Transform points? No, because that's what the other ones are. So these points are going to be like the point value from 0 to 1. So maybe we call, yeah, I understand. I can't type either. We're just gonna call them, pixel points. No. Whatever. No. Whatever. I'm just calling them balls. Screw it. Bad names aside, that's what I'm calling them. Okay, let's go. So these are going to be all the balls that we're going to be modifying. Not going to worry about it too much. How should I implement an ASCII ray tracer? To be fair, I don't think this is impossible. I think you can do that if you want to. But it's just not going to be that great. Anchors? Why would they be called anchors? Okay, so what we have here is we have the ellipses being drawn. And so what I want to do is I want to push back each of these guys too. So what I'm going to do then is I'm going to go ahead and create all of these ASCII objects at their appropriate location here. So we're going to say balls of I is going to be equal to, yeah, I don't know either. I don't know. Let's see. We have 3 legs, so we're just going to say we have a location for each of these points. So let's go ahead and define the location for each of these points too. So we're going to say vec location is going to be equal to, and basically the location is going to be this guy over here. So let's move up here again. And so since we have the location, we can also change the color. So let's go ahead and here's the location there. Oh, I see what I did wrong. Let's go ahead and add in a guy there. And let's also change the color. So in a very similar way, I'm just going to have the ball color up here. Let's go ahead and add that. So yank. And let's go ahead and paste it down here. Okay, so now we have the color. And we should just be able to create the ball by saying balls is going to be equal to std make shared. And we're just going to say ellipse. Come on. There we go. And then I'm just going to read in basically all the things that we have. So ball color, location, vector 0, 0 for rotation, and then fill color of 1. All right. And this should create a random distribution of points. So I'm going to pop down here and I'm just going to comment this guy out there. 1 second. And then I'm going to grab the Barnsley transform function here. The random number of points that we're going to create, let's just do 1,000 points for now. And the transform type we're just going to say is 1. It doesn't really matter too much right now. And let's pop down here, pop up here again. So we have all the objects being created. Now we basically have to add all these objects to the world. So what I'm going to do at the start actually is I'm going to create a few layers. So it should just be like world.add layer. Yep. World dot add layer here, do it twice. I'm sorry, look, I'm really bad with naming things. It's totally a safe for work stream. I'm just horrible with naming things. Okay, so we have this. Now let's go ahead and add all the objects in here. So we're gonna say world, worlds.add object. And the object we're gonna be adding in is going to be the balls of I. And we're gonna be putting it on layer 1, I believe. Okay, so this should, in principle, create a random distribution of points, I believe. So let's go ahead and compile that. See if it works. It does. Let's run Barnsley. And then we should just create a very quick video with just a random distribution of points. And we can work from that. Give it a second to run that. Call them attraction points. I was actually looking for a link to someone I encountered years ago. Why would you call it? I don't know. I don't know, man. I'm so sorry. I can't name anything to save my life. I called the other one ball and the other one point. Maybe I should call them locations, or I don't know. I don't know at all. I found a different one that someone did. What do we have here? ascinema.org. Ooh, this seems nice. Please play. Raycaster, all right. Oh, this is a raycasting thing. Yeah. Ha ha ha. Of course. Super nice. All right, let me go ahead and pause this guy. It is. All right, cool. Let's take a look at MPV. We should see. Not that. What did I forget to do? We added all the objects. And... oh, I forgot to update the... yeah, I forgot to do this. Let's try that. Pop up here. And let's paste it down here. I'm sorry, I forgot to update the world every time step. Let's try this. /Barnsley. And give this guy a go. Raycasting is a step in ray tracing. Yeah, I guess that could be true. Let's see. But by the same guy? Ha. Oh, this guy's amazing. Let me see if I can... oh, dude. Whoa. All right, I am, who's this guy? California. He said I'm following this guy. He seems cool. All right, that was super cool. All right, I'll give this guy a second to update. I just had a computer graphics course where half of the course was ray tracing. Oh yeah, that's totally fair. That's impressive. Note, not the same guy that did the awk implementation. Oh, okay, fair enough. But still, super cool. All right, give this guy a second to finish running. I'm sorry it's taking so long. It's taking a while. It is what it is. I'm not too worried about it. I think it's just because we're doing super high resolution images. We probably should be doing lower resolution images, but hey, it is what it is. So we're gonna run MPV. That is not a random distribution of points, dog. I don't understand. I don't understand at all. Okay. Let's try running it one more time. Am I running the wrong function? Barnsley transform. Cam world 1001. Yep. I'm not sure what's going on here at all. Pop up here. I did, however, realize one problem here. Let's go ahead and change this to 5. Something like that. Well, let's do, yeah, 5 is fine. That was actually the size, not the rotation. I don't know why I thought it was rotation. World objects add. We're adding all the objects to the first layer. The problem is we're for some reason not generating the right video. The awk version can be used to run Wolfenstein. Oh, okay. Interesting. Nope. Alright. Maybe the compilation isn't working? Oh, you kidding me? Yeah, well, that would be the problem then, right? I was compiling the wrong code. Yeah, okay. See, this is more what I was expecting. Okay, so here's all the errors with the Barnsley code. Let's go ahead and fix it up. Shared pointer isn't a thing, it's shared PTR. Let's see. Ellipse, let's go ahead and write this, go over here, try compiling that. Clear here. Let's go again. Gives us a few errors, let's see. PT was not declared in the scope, that's because I believe it is PT S of I. And we do the same thing down here. Okay, what do we have here? Error, I expected that, so we're going to go to 25. Actually, I believe that's fine. So let's try clearing again, and let's running that. We got another error. This is expected. Oh, okay. Oh, that's because this is here. All right, what's your error now? Oh, that's incredibly hard to figure out. Let's go ahead and clear a couple times. Clear, 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 clear. There. Yeah, I have no idea what your error is. No matching function, call for ellipse, color. That's because I need a... No, I don't know what I need, actually. Let me take a look at the make shared down here. Add animator, make shared ellipse, ball color, vector. Oh, I forgot one. Yeah, I definitely forgot one. So now we have 0 for rotation. And then we have 1 for fill. Alright, let's give this guy a go. And that should compile. Then we should run Barnsley. And then we run the last MPV. And hopefully this works. Okay. What do we have here? Husky, I think the case looks pretty good. It's just super wide, which is annoying. You could go fractal design. We have a single green line at the bottom of the screen. Okay. I think I know why. Yeah, I think I know why. And it's not going to be an easy fix. So I'm going to leave all these points at the bottom of the screen, and we'll work with them from here. So we have all these points, all these objects being added to the world. But what I'm going to probably do, I'm going to go ahead and add in a balls of I, and we're going to add an animator. And the animator is going to be, hey Folster, how are you, man? And the animator is going to be vec animator. All right. And what we're going to do is read in, I always have to look up this notation. It's going to VI, actually, I guess the only thing we have here is sierpinski.cpp. VI sierpinski. CPP is what I was looking for. 1 second. Pinsky.cpp. And let's take a look at animator here. Okay, so that's the notation that we're looking for here. And so what I'm going to do is just make all the random points appear at the same time. I'm not too worried about it. This is going to be 0 to 30. And then we're just going to say ball of I dot size. And we're going to be changing the size from vec 0, 0 to vec 5, 5. Vec 0, 0 to vec 5, 5. Okay. And that there, and change this to 0, 0. Okay, so now we have the world added objects. So now all we have to do is move these objects. So I'm going to, I'm going to DD there, and I'm going to have another guy here. So for int I equals 0, I less than point size. Then we're going to do plus I, pop down here. And we're just going to do the add objects here. So it's going to be world dot add object. And it's going to be balls of I on layer 1. Something like this. I've been here. I'm sorry you have. I'm just being an idiot. I'm so sorry. I saw the oh bother and I was like, oh Folster, hey, how are you? And it's like, what? I don't know. I don't know what I'm doing anymore. I'm just talking. I'm so sorry. Cubish case, super inconvenient if you have your PC over your desk. Over your desk. Yeah, I'm not sure what we're talking about anymore. Okay, so let's pop down here. The next thing I need to do is basically move these guys. So we're going to go through all the points and we're going to transform all these points. So we're going to say, basically depending on the int t type that we're reading in. So if if t type is equal to 0, actually we can probably just do a case here. So let's do switch of t type. And let's just do case 0. And we're going to break it. Yank to yank. Paste, paste, paste. So this is going to be case 1. U there. 1, 2, 3. And then we should have like a default case. But this should be fine. Let's go ahead and compile that guy. Barnsley. Ooh, hello. Not what I meant to do. Yep. Okay, so now we have the case 0, case 1, case 2, and basically what we're going to be doing here is we're going to be transforming our points and then giving them a new location. Giving them a new location. Yeah, I think that's okay. So we have the vector location where they were before. Let's go ahead and define that. So we're going to say vec sorry for the on here. So we're going to say vec loc previous is going to be equal to this guy here. And then we're going to create a another vector afterwards. So we're going to do d here. And let's go ahead and transform our point. In fact, we can probably just grab these transformations from down here, I believe. So we're going to say point is equal to this. Something like this. Okay, so let's pop up here. Paste it there. And we're going to say points of I is going to be equal to that. Something here. Let's see. We're talking about cube cases over here. I don't know. I don't know anything about this. So let's see. Something like this should probably work. I don't know. We'll see. And then at the end here, we're going to say yank to yank. Paste it down here. And we are going to say location after. I don't know. And we're going to add the appropriate transformation. So let's go ahead and get this guy working. So the next guy, we're going to do yank to yank here. Paste it up here. Another one down here. Yank to yank. There, and then finally one over here. And let's go ahead and get this guy all up and running. Okay. And it's gonna be points of I. We're gonna have to change this guy. This guy. Actually, I'm just gonna change them all now. Here, there. Sorry, this is. It's a bit of grunt work, but we're gonna get there. There and here and there. Okay, so it looks like it's 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, something like that. So we can probably do the same thing down there. Okay, nice. So this should update all the points. We should have a location before and location after. So now we basically have to say balls of I add animator vec animator. Nice. And then what we're going to do is we're going to add in the time frame here, which I'm going to say is going to be from, oh, let's say it's from, it's probably going to be a second long animation. We had all the points being created from 0 to 30, so let's say it's from 60 to 120. Something like this. And then we're going to say balls of I pointing to location. Now the question is it loc or location? I don't remember. Let's go into vi .gathvl and let's look for viz test. Let's look for location. Yeah, it is full out location. Okay, then we give it basically the start and end points. So we're going to say location previous, location after, and then we end that guy, and hopefully this animator is added, the object is added, and we should be able to go from here. Let's try compiling that guy. Seems to work. We're going to run Barnsley, and let's see what the animation looks like. The points look like stars in the night sky. Yeah, we'll see. So Christmas lights, we're kind of going for something like this. I'm hoping that this turns out the way that we're expecting. So let's do a quick MPV. Okay. That was incredibly... Let's try here. And let's do transformation 0. And we'll see how this goes. So we're going to do G++. A photon checks into a hotel, and the porter asks him if he has any luggage. The photon replies, "No, I'm traveling light." Ha! I had a similar case where there was this one time I was on Omegle. Don't get me wrong, I used to really like Omegle before it went kind of crap. This was like 5 or 6 years ago. And I just talked to someone at random. And the funny part was that when I was talking to this person, I was trying to convince them that I was a photon. And so like they were asking about like, you know, age and height and all this kind of stuff. And I kept making references to being like incredibly fast and incredibly light and all this kind of stuff. It was really funny internally, but it was really, really, probably really cringy in actual practice. Okay, so what I'm going to do here is I'm going to pop up to the top and I'm going to make this random distribution a bit clearer to see. So let's see, we want to change the point location here. So we say 0.5 there plus, so let's do plus 400. And over here, let's do, we're going to make it 400 by 400. And actually, let's make this, yeah, okay, so let's do plus 200. And let's do minus 200. Okay, so we're going to center this random distribution of points, plus 400. Okay, so this is going to be their initial location. And I'm just going to grab this guy and yank to yank and paste it here again. And paste it here again. And we're just going to change this to after. DDDD. And we're going to do the same thing over here. Okay, DDDD. Something like that. Same thing over here, but I think it requires a few more spaces. Okay, so let's give this guy a go. We are going to compile it. Barnsley. And we should see kind of a more random distribution of points, and we should see this animation kind of moving. I forgot Omegle was like the time waster back then. Yeah, I'll be honest, I did spend some time on Omegle. It was fun. So let's do MPV. Okay, so I think I'm doing something wrong with this random distribution of points. So I'm gonna say points of I am totally doing something wrong with this random distribution of points. Let's try this. G++ /Barnsley MPV. I was only giving it an X position instead of a Y position. That totally explains what the deal was. So now we should see a random distribution of points. Hopefully. There we go. There's a random distribution of points. There we go. That's what I was expecting. Okay. So that's the first transformation. Let's just take a look at all these transformations that we have, and we'll try to modify them. So there is 0. Here is 1. So let's do G++ /Barnsley, and then we're going to do MPV. So we have a random distribution of points, and then we go from there. I think everyone really liked the video. Did you post the video in Discord? Yep, that's what I expected for the second transformation. Nice. That's what I wanted to see. Now let's check out the the third transformation. So let's do G++ /Barnsley. This is turning out perfectly. So we have a random distribution of points, and we're showing what each transformation does. So the first transformation we saw generally put everything into a line. That's the stem of the Barnsley fern. The next transformation we saw generally moved everything upwards, right? So that's going to be the successive leaves of the Barnsley fern. So now let's take a look at this guy, which should be... Boom, look at that. It turned everything over here to the lower left-hand corner, so that's going to, or the upper left-hand corner, so that's going to be the first kind of leaf on one side. And now we should have another one that's bringing it over the other way, which should... Ooh, man, this turned out way better than I was expecting. So G++. And this last bit should be the final leaf, which is moving it over this way. Come on. And then the idea here is we create a leaf, or we create a stem, we create one transformation that's going one way, one transformation that's going another way, and then a final transformation that takes this object that we created and basically pastes it progressively upwards. And that's what you got. Nice. So let's do MPV. Okay. That one worked slightly differently than I was anticipating. Why did it flip? Here's a random distribution of points. I think if we put all of them together, we get a better understanding of what it is that we're doing here. Dang, okay. We'll keep looking at this. The one thing I do definitely need to do is change this transformation to transformation type 0 and make sure that after the transformation it is centered, because right now it is not centered. So let's do G++ /Barnsley. Hi, Plessy, I'm finally done with what? With the paper? Oh, cool. Dude, fantastic. The 3D printed one? Oh, dude, super cool. If you could if you can, feel free to post the paper in the Discord chat. We'll take a look at it. MPV. Okay, so my main problem with this is that it is kind of sort of moving to the lower right-hand corner or left-hand corner, and it shouldn't be doing that. It should be moving to just the center of the screen. So I'm trying to figure out why it's doing that exactly, and I'm not really sure. So what we're doing is we're subtracting. So after the transformation, the point becomes whatever point it was. It just becomes 0 in x. Becomes 0 in x, and then it increases a bit in y, right? So we're saying world.size.x minus 200, right? So let's say the center of the screen is 500. We're subtracting 200. Oh, actually, I think this is correct. We want to change this such that that is here. That. So we're going to do G++ /Barnsley, and this should make it so the stem is at the center of the screen. So MPV, once that's done. And now let's see if we can figure out what's wrong with that last transformation, and then we can probably go from there. Yeah, this is what we want. Yep, okay, I understand now. We want this to be centered. So let's change these random distribution of points such that they're generated from -1 to +1. So we're going to take this random number and we're going to multiply this by 2. And then we're going to subtract 1. Times 2 times 2 minus 1. We're going to do the same thing over here. Yep, okay. So now we should be centered, and let's go ahead and change this to what we want it to be, which is here, and change this to what we want it to be, which is here. And let's actually make it a bit lower in y. So we're going to drop this guy to plus 500 again. Yeah, let's make it plus 500. Okay, so we're gonna do G++. 1 second, dot slash Barnsley, correct, and then MPV once that's done. Guys, I do have a bit of an unfortunate thing to say here. I have to leave a little bit early today at 6:50-ish. So I gotta leave in about, what is that gonna be, 15 minutes or so? So I just wanted to make sure that was clear. Okay, the distribution is a bit larger now. And I think actually what we want is just, let's see, let's try this real quick. So this should be at the dead center of the screen. So we're gonna do G++ dot slash Barnsley, and then we're gonna give that guy a go. What do we have here? I tried to eat a watch yesterday, but I had to stop. It was too time consuming. You drop a piano down a mineshaft and you get a flat minor. Oh man, that could be interpreted in a way that's kind of... So there's a random distribution of points. Yep, there's the stem. That's what I was expecting. Nice, okay. Yeah, nice, okay. So let's see, what I want to do then is drop the Y value down a little bit. Maybe... Actually, let's just change this to make it so the screen is slightly smaller. So we're going to do 200 by 200. You there. 2, 2. And there's going to be 2, 2 here. And we're going to drop the Y value just slightly. So we're going to say plus. Oh, I see the problem here. It should be plus, let's give it plus 200 minus 200 here. And we're just going to put that everywhere. So it should be plus 200 minus 200 here. I believe there. Oh, you there. There. Yep. And then down here too. So we're making the screen slightly smaller and we're giving it an offset. And hopefully this should solve our issue. So let's do Barnsley. MPV. Okay. And this visualization, I think, turned out pretty well. So this gives us a better understanding of what each of these elements are that we're working with. Why did the right triangle go to the beach? It was 90 degrees. Yep. Okay, so there's the initial stem. So let's look at the other guys too. So we're going to take a look at transformation 1 now. Let's go ahead and do G++ dot slash Barnsley MPV. And what we should see here is we should see our random generation, our random distribution of points moving upwards. Did you hear about this? Wait, so this should move upwards. Nice, upwards and slightly to the right. And then we see that happening a lot. Let's see. Did you hear about the scarecrow who won the Nobel Prize? He was outstanding in his field. So let's do 2. The only transformation I don't think I fully understand is... Yeah, the only one I don't think I fully understand is the final transformation. So we're going to take a look at that one too. Again, each of these transformations that we're seeing are different bits of the Barnsley fern. So one of them will create the stem. That was the first one you saw. The next one creates successive branches going upwards. The next one creates one leaf, and the other one should create the other leaf. And now the question is, how do we explain the Barnsley fern in a more intuitive way? And so this one creates one leaf. Oh, this looks like the bottom right-hand leaf is actually which one this one's creating. Yeah, so this is creating the bottom right-hand leaf. And then the next one should be creating the upper left-hand leaf. 3, write this, go over here. And now I'm going to check with Wikipedia to make sure that's true, but I think that's correct. Okay, so let's take a look at what we have over here, Barnsley fern on Wikipedia. What do we have? This coordinate transforms 7% and maps any inside point of the leaflet or pinna represented by the blue triangle to a point inside the corresponding triangle on the stem. It maps any point on the inside leaflet represented by the blue triangle to a point on the alternating corresponding triangle across the stem by flipping it. Oh, this is actually slightly different than what I was expecting. So the first coordinate transform is chosen 1% of the time and just maps any point to a point in the first line segment at the base of the stem. So this part of the figure is first to be computed during the course of iterations. So basically, yeah, you just create the stem with the first transformation. The second transformation, this coordinate is chosen 85% of the time and maps any point inside the leaflet represented by the red triangle to a point inside the opposite smaller leaflet represented by the blue triangle in the figure. What? I don't think that's quite right. Successive small leaves, largest left-hand leaf, largest right-hand leaf. Yep, that's what I was expecting. This is the easiest interpretation. Yep, that's the interpretation I'm going with. Cool. Largest left-hand leaflet, largest right-hand leaflet. So this should be the right-hand leaflet, the one I just generated. Let's take a look. Yeah, I'd believe that's the right-hand leaflet. That's fine. I'd believe that. Cool. Cool, cool, cool. Now the question is... Okay, so we can make this a little bit better. What we can do is we can create a random distribution of points. Let's see. One random distribution of points that creates a stem, another random distribution of points that creates one leaflet, then another leaflet, and then finally a last distribution of points that creates a successive leaves going up. And so there's definitely ways to work on this. There's a new fad in town about making brews and books. It's mostly a novelty. It's mostly a novelty, though. My mom brought me this cool Rubik's Cube that you only move by twisting centers and corners. Huh. Hey, JSPP, how are you? Let's see. Ruhai, yada yada. Okay, cool. I think I'm caught up. Okay, so I think actually what I want to do here is I want to... Actually, what do I want to do here? So we have all 4 different transformations for the Barnsley fern, and we have a good understanding of what these transformations are actually doing, and we have a pretty good visual representation of what it is that they're doing. Now, the thing is, starting from a random distribution of points, let me go ahead and take a look at what happens with our actual Barnsley fern. So let's go ahead and modify this guy. Oops, sorry about that. Here. Move up here real quick, and let's modify our random distribution of points such that... Oh, the point always starts at 0, 0. Oh, okay. So we do need to change something then. So our point initially starts at 0. All right, we need to think about this, right? Let's see, what do we have here? Open link. Oh yeah, I think I've seen one of these before. Okay, so our point initially starts at 0, 0 for the Barnsley fern, and it builds itself upwards. For the rest of the fern, right? And that's fine. We have an understanding of what each of these transforms do. Now, the problem is that because we're starting with a random distribution of points, this random distribution of points for the right and the left leaves are not necessarily where you're going to be starting from for that leaf. Does that make sense? You don't start from a random distribution of points. You start from 0, 0, and then you build the leaves up from there. Oh, I'm sorry about that. So what we should probably do is we should probably perform the first transformation, and then use that distribution of points to create the second and third transformations, and then the fourth transformation from there. So we shouldn't have this ability to read in the transformation type at all. We should basically do the first transformation, then the second transformation, then the third transformation, then the fourth transformation. I think that's how it would be. I would actually be kind of funny to link our paper. Love seeing James read Dutch. Ha, I'm sorry. Now, unfortunately, guys, this is as far as we're going to get today. I do need to head out just a little bit earlier today, and I apologize for that. So I think maybe this is where we'll end. Let me go ahead and do a quick right here. And let me say to do modify such that we perform a first the stem transformation, then the right and left leaf transformation transforms and then the successive leaves upwards. Okay, so we'll see what we can do. I know I'm really trying to get this video out on Sunday, so we're a bit late there, but I think we can still make it work. I think we can still make it work. Ah, shoot, I hit the microphone again. Anyway, guys, that is it for the day. Let me go ahead and commit this to GitHub, git add, let's do git commit, barnsley.cpp, -m, adding more, I guess you could say visualizations for Barnsley Firm. Okay, so let's go ahead and see who is online. Git push, origin master. So this should be available on the Simuleos repository now. I might work on this throughout the day, but basically the heart of what we're doing is there. So there might be some stuff here or there that we need to work on. Again, if you haven't seen Fulster's video yet, check it out. I'll be checking it out soon. Let's see. Oh, Bother's live. We can bother Oh Bother. Skyleys, we bothered them last time. Yeah, let's do Oh Bother. Hey, Determinist. Unfortunately, I think we're heading out for now. So guys, thank you so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. We'll be back tomorrow. I'm probably not working on this animation. I'll probably work on this animation tonight when I get back from work, while also doing the voice recording and the editing and all that kind of stuff. So we have the video ready so that tomorrow we can basically work on our fractal Christmas tree, try to get this guy completely done. And then once that's completely done, we have something working for the video that I want to have out on Sunday. And let me go ahead and check this straw poll. Straw poll, where are you, dog? So check the results here. I'm guessing what we're going to be doing is we're going to be creating the chapter first, then the video. How did we get 54 votes on this? Did someone just keep voting? Who just kept voting? Let's see. Sneaky bit to host coding with ethanol. Oh, are they live? Yeah, we can host them. Where are they? Am I not following them? Oh, so let's take a look. So browse. Coding with Yeah, we could do this. Yeah, fair enough. Let's go. Oh wait, are they live? Oh wait, coding with ethanol. Wait, are they live? That's the question. I think they are. No, this looks like a video. I'm confused. Oh, now they're live. Good. I'm sorry, I screwed up. Okay, so we'll go ahead and host them. It's fine. It's not manipulating the vote. We usually host different people. Okay, we will be doing chapter revisions on Monday, undoubtedly. Let's take a look at the straw poll. So it looks like most people are okay with the... Oh, no, someone really wants a chapter first, then the video. But it looks like there's 43 votes for chapter first, then video. Guys, did someone just, like, vote? JSPP, who did this? Oh, my gosh. If we want to do the chapter first, then the video, we have to significantly rethink our schedule. We really need to rethink the schedule. IP duplication injection? No, but we have IP... I'm not asking anyone. I'm just trying to figure out how we can work the schedule now if we do... I'm not asking anyone. Okay, if we were going to do the chapter first and then the video, we are going to have to do things a bit differently. So I need to rethink that. Because honestly, if we're going to put the chapter down first, we're in a lot of trouble there. But I really don't understand how we got 54 votes on this when we only have 24 people watching right now, if that. We have 24 people watching right now. So like, I really have the feeling that someone manipulated the vote here. Let's put the video out first. We delay the video if it's ready. Yeah, I don't know. That's the thing. Okay, so we'll talk about this again tomorrow. Okay, we'll see what we can do. All right, guys, thank you so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos. Again, when we work on the Fractal Christmas tree, I'm hoping to get most of the video done this afternoon. We'll see how things go. There's a lot of stuff left to do. And we'll just see what we can do. So thanks again, guys, and I will see you next time. Bye, guys. Hey, happy little rat. Sorry that you came in at the end there.